Up till now, the things that we've talked about in modeling an epidemic system has actually been fairly trivial. The equations that we came up with that describe how the variables, the number of people in each population changes over time, are simply summative type things. They're equal to what it was before, plus however much it changes. And these actually come directly from, so they're exactly a map onto the system diagram in the first place. So everything that you see in the yellow highlight is really just different representations of exactly the same kind of thing. And in fact, that fits also into this part of the table. So all of that stuff is very intimately connected to this, in fact, pretty qualitative understanding of how an epidemic spreads. The thing that makes it quantitative, the thing that makes it realistic, is having better information and a better way to get our head around the rates. So these are needed and we need a more explicit way to do those to make this a quantitative description. So figuring out transmission rates, figuring out recovery rates, and figuring out death rates, the number of people who enter or leave different populations in any time step, that's the hard part of building any model. And we can let's start with the transmission rate and think about what this ought to depend on, and then postulate. This is where your scientific creativity and where you need somebody who's not a modeler, but somebody who's an epidemiologist, or somebody who's a biologist, or somebody who understands virology, to actually give reasonable expectations for how these things occur. So the transmission rate, the number of people who acquire the disease in a time, in this idea where we have a population where infected and uninfected people are intermingling, and that transmission occurs through contact between those two groups, has to be represented as simply a probabilistic kind of way. So if the number of people who are going to get infected is simply equal to the number of people who could get infected, so the susceptible population at any instant in time, times a probability. So a probability that they become infected. So a probability is a number between 0 and 1. And so the number of people who get the disease in any day, or in any week, or in any what time step we use in our model, is simply a less than 100% fraction of the number of people who could acquire it. Again, a fairly simple statement, but in order to write down an appropriate expression for this, now is where we actually need to start understanding something about how the system behaves, how viruses spread, and that kind of thing. So because it's a contact-based transmission, at least in this case, the probability of infection should depend on a couple of things. It should increase as the contact between susceptible and infected people increases. So as the population of infected individuals goes up. So this should increase as the number of infected people become a larger fraction of the total population. So as the number of infections go up, so also should this probability. But it shouldn't only depend on that. It also has to depend on how fundamentally infectious this disease is. So this is an example of a variable affecting a rate, but there is a fundamental ability of this to infect others. This disease has a particular transmissibility, and nobody knows exactly what it is. And I don't even know what to call it. Ability to infect, we can call it a transmission rate, a number of people. Infectivity. I'm making up words for this because I'm not an epidemiologist and I don't know what these things are actually called. But so this is a parameter. It's something that you would fix in the beginning of a simulation and run it, and you would get some results, and then maybe you could change it until you got output that matched what you observe in the real world, and that actually would be one way to discover what the fundamental infectivity or infectiousness of this disease is. But that'll have to be a parameter that has to go into this. And so what that means is that the transmission probability, or not the transmission probability, but the number of people who become infected is going to be equal to the susceptible population times this transmission infectivity times the number of infected people divided by the total population. That becomes actually a deterministic equation that we could then use. So this is something that we know. This is something that we can input. This is something that we know because it's a variable. This is as a function of t. N is not. N is the total population. And it's fixed as an input parameter. So all of those things, because they're known, this becomes something that we could calculate at any one time. If we want to take a look at the other ones, that's the hard one. The recovery rate, or the number of people who recover in any particular time, it's been reported that it takes about a week and a half, 18 days or so, on average, for a person to recover from initial infection. So it's about 18 days recovery time. Now there are some pretty sophisticated ways to incorporate this, but it turns out a pretty simple one that gives reasonable results is to say that 1/18 of the infected population recovers on any one day. That'll average out so that the entire population will recover in an average of 18 days. So this simply becomes the number of infected people at time t divided by 18 if we're doing this in a one-day time step. So that's actually pretty trivial. The death rate has got to be some fraction of the people who are infected. So this will be some infected people at any one time times some mortality rate, and this is going to be another parameter. So this 18 days, this is a parameter, but it's informed by studies. This is a parameter that isn't actually particularly well known, nor is this one here. So the parameter that is the single day mortality rate may be something that we will use as a tunable parameter so that the simulation matches reality as best as we can. I mentioned that this one is informed by reports about how long it takes to recover. There have been other studies that have looked at this transmission infectivity, or the number of people that acquire the disease, the number of people that any infected individual will reinfect in a day. And there have been reports published that place this in a range from anywhere from, I wrote these down, so anywhere from around 0.2 to around 4 or over 4. So it could be that any one person infects, any 5 people infect one new person, or one person will infect 4 new people. And depending on the conditions, it may be somewhere within that range. And when we build a simulation, obviously we can type in any number that we want as a parameter and see what implications that has for things like how many people are dead after 120 days.